Hard disk drives are rapidly becoming the mass storage media of choice for microcomputer users. They are faster than floppy drives and store much more data. In this presentation, we will demonstrate techniques for testing and aligning hard disk drives. After viewing this tape and completing the accompanying workbook, you will be able to test a hard drive and detect any failures that alignment will not correct. In addition, you will be able to align both 8X300 and WD-1010 based hard drive controllers and adjust the motor speed on hard drive bubbles. Finally, you will be familiar with the basic operation of a hard disk assembly, which we will discuss next. Unlike floppy diskettes, Winchester hard disks are not interchangeable. The disk, along with heads and motors, are sealed in a case called a bubble. The mechanism within the bubble is, however, very similar to a floppy drive. In place of the floppy diskette, there are several rigid platters coated with magnetic oxide on both sides. A spindle motor rotates the platters at a very high speed, usually about 3,600 RPM. Read-write heads, one for each recording surface, write to or read from the platters. The heads are ganged on a shaft driven across the platters by either a stepper or servo motor. This arrangement is very similar to a floppy diskette drive, except that there are more heads involved. One difference between floppy and hard disk drives is that hard drive heads do not contact the media during operation. Hard drive heads are aerodynamically designed so that, as the spindle motor turns, they lift or fly off the surface of the platters. This makes greater rotational speed possible by reducing friction and wear on the platter. However, the mechanism requires careful treatment to prevent accidental scoring of the media. Spindle motion creates an air cushion that the heads fly on. When the spindle is still, the heads actually rest on the media. Moving the stepper motor will cause the heads to scrape the platters and damage the media. To prevent accidents of this type, some drives have a lockdown bracket that keeps the platters from rotating. You must use these brackets when shipping the unit. Never apply power until the bracket has been removed. Many operating systems also provide a command for moving the head to the innermost track for shipping. This can prevent damage of the drive's boot track when the drive is moved. The technician must be careful never to move the stepper unless the spindle motor is turning. For example, do not use the hard disk exerciser diagnostics or manually step the motor unless the spindle motor is turning. Also, never rotate a spindle motor backwards. The shape of the heads will not allow them to lift if the platters are spinning in the wrong direction. If they do not lift, the heads will scrape the media off the platters. Never bump or jar a hard disk when it is running. Be especially careful not to drop or lift the unit. Vibration of any kind can cause the heads to hit the platters, damaging both the heads and the media. The heads fly at a height of about 20 microns over the media's surface. Relatively, a speck of dust appears to be the size of a boulder. Dust particles can wedge between the heads and the platters, damaging both. To prevent this problem, hard disks are manufactured in a clean room where these particles are filtered out. The mechanism is then hermetically sealed into a bubble which prevents dust from reaching the mechanism. For this reason, the technician must never open the bubble unit. To maintain the clean environment, the Winchester drive is sold as a fixed disk. That is, the media is not exchangeable. Also, Winchester fixed disks have very few mechanical adjustments. Some bubble assemblies do have a track 0 adjustment. The technician must never attempt to adjust it, however. Each bubble is shipped with a media error map, which is a list of any flawed tracks on it. Track numbers are relative to track 0. So if we change its position, we also change the positions of any flaws. We cannot recreate the media error map in the field for two reasons. One, we have no way of knowing how far track 0 has moved, so we cannot modify the old map. Two, we cannot recreate the map from scratch because we don't have the proper equipment available in the field. Many hard disks have a motor speed adjustment potentiometer which varies the bias to the spindle motor and changes its speed. This is the only adjustment that we normally make to the bubble unit itself. In addition to the bubble unit, all hard disk systems have some type of controller board. In Tandy systems, it is mounted inside the computer or in the primary hard drive. The hard disk controller is an intelligent peripheral device as opposed to most floppy disk controllers, which require step-by-step instructions from the CPU. To place data on the hard disk, the computer need only tell the hard drive controller that it wants to write data and to which location. Then, the CPU sends a sector's worth of parallel digital data to the hard disk controller's buffer. At this point, the computer is done and the hard disk controller takes over. First, it converts the parallel data to serial time-encoded format called Modified Frequency Modulation, or MFM. A write clock provides a time reference for this data. The controller sends this information to the hard drive logic board. The drive logic board converts this digital information to analog current reversals and sends them to a read-write head. As the current flows through the head, it forms magnetic domains on the platter. These domains are simply areas where all the magnetic dipoles are oriented in the same direction. The time relationship between the domains defines the logic levels that they represent. To retrieve data from the drive, the computer must first tell the hard disk controller that it wants to read a certain sector. The controller tells the stepper to seek a track and then enables the read circuitry. Once the drive reaches the correct track, it must find the beginning of a sector to determine if it is the one that the CPU wants to read. Since the data is recorded in a time-encoded format, the controller uses a time-sensitive circuit to find the start of a sector. A string of zeros is the first data recorded on each sector. In MFM format, a string of all zeros or all ones has a characteristic high frequency. A one-shot on the controller board detects this high frequency and increments a counter for each pulse in such a string. To assure that the one-shot detects only high-frequency data, we can adjust its period. If 16 of these fast pulses appear in a row, the counter produces a signal called data run, or D-run. This signal tells the controller that the beginning of a sector may have been detected. The controller then begins to decode the incoming data. The first step in this process is to provide a read clock that has the same phase and frequency as the clock used to write the data. A voltage-controlled oscillator, or VCO, synchronized with the incoming data stream provides this clock. An error amplifier synchronizes the VCO to the incoming information. It compares the data stream coming from the drive with the output of the VCO and corrects the VCO if the two are not the same. Since the data stream is not at a fixed frequency, the VCO must be able to lock on a wide range of input frequencies. This feature can lead to problems such as locking on to incorrect frequencies. To prevent this type of problem, there may be adjustments in the VCO and error amplifier circuits, including incoming data pulse width, VCO bias and output frequency, and dynamic error reduction. A data separation circuit compares the incoming data to the read clock and determines whether the pulse represents a 1 or a 0. The data is then converted into parallel bytes and stored in the controller's RAM buffer. Once the entire sector is read, the controller will inform the CPU that it is ready to provide the information, and the CPU will read it in. As you can see, the most sensitive part of this circuit is the section that reads the time-encoded data from the drive logic board. Hard disk controllers often have adjustments in these circuits to increase their reliability. Not all hard disks have all possible alignments, and the adjustment procedures vary with the controller. Check your diagnostics or documentation for the correct procedures, test points, scope settings, and readouts. On some boards, the incoming data passes through a pulse-shaping one-shot. The period of the one-shot may be adjustable so that the data pulse width can be matched to the VCO's output pulse width. Many controllers also have an adjustment for the D-run one-shot, which detects high-frequency data that may indicate the beginning of a sector. The method of adjusting the D-run one-shot varies, depending on whether it is separate or part of an LSI device on that controller. The VCO bias and output frequency are adjustable on most controller boards. Some have a coarse adjustment, usually a variable capacitor, and a potentiometer for fine-tuning. Finally, some designs allow the technician to adjust the error amplifier's output for a minimum number of corrections during operation. There are several situations in which we must perform these adjustment procedures. We need to check the alignment during routine computer maintenance. If we correct misalignment early, we may prevent loss of customer data. We must also align a hard disk whenever a bubble or controller is replaced. Alignments vary from machine to machine, so we must check each unit when it is installed. Finally, align a hard disk anytime it is failing or operating intermittently. In many cases, misalignment is the unit's only problem. Always perform alignments in the proper order. Check the motor speed first by measuring the period of the index pulse with a frequency counter. Remember to select the drive that you want to check if you are taking the reading on the controller board. We check and adjust motor speed first because the rotational speed of the platters affects the data transfer rate. Incorrect motor speed can result in incorrect readings for the data pulse width, error amplifier, and derun adjustment. The next alignment to make is input bias and the output frequency of the read VCO when no data is being read. The purpose of this adjustment is to make the VCO output frequency as close as possible to the nominal read data rate. Remember to turn the drive off for 30 seconds and then back on to verify that the VCO locks on to the correct frequency. Otherwise, it may operate at an incorrect rate, which will make it impossible to decode incoming data. If the frequency is not correct, readjust the VCO. Make sure that the bias is in the center of its range. The VCO frequency is the only adjustment that we can make with the hard disk idle. All other alignments require read data input. To assure good read data input, always reformat the diagnostic track before attempting these adjustments. If the drive has adjustable data pulse width, align it next. The pulse width of the incoming data can affect the derun one-shot and the error amplifier operation. Next, set the derun circuit to trigger on a string of zeros or ones, but not any other type of data stream. If derun is misaligned, the read circuit may never be enabled. Dynamic error amplifier adjustments require read data, so derun must be correct before the error amplifier is aligned. Then, align the error amp so that there are as few corrections as possible to the VCO during operation. To observe the error amp in operation, place a scope probe on the bias input of the VCO. First, make sure that the error amp is operating. If the bias voltage is at 5 volts or ground, either the amp is badly misadjusted or the circuit is defective. Adjust the control pot for a voltage in the center of the specified range. The voltage will contain some spikes, each of which indicates a correction to the VCO. Try to minimize the number and width of these spikes. Then, fine-tune for an equal number of pulses above and below the average voltage. Before assuming that the controller alignment is correct, check derun and data pulse width on each secondary drive in the system. Next, choose the Read Current Track option and observe derun and data pulse width. If these alignments appear significantly different, recheck the motor speed, reformat the drive, and try again. This procedure assures that the controller is communicating with all the drives correctly. Always check the motor speed on each drive just before reassembling it. This allows you to detect motor speed drift. Although not all controllers have all adjustments, there are some rules that apply to all hard drive alignments. Always check the hard drive for mandatory modifications. These can affect the results of your alignment and the reliability of the drive. For the best performance and customer satisfaction, make sure that all modifications are done. Warm up the hard drive for at least 30 minutes before alignment to accommodate heat-related media expansion and component drift. A drive that appears correctly aligned when it is cold may not operate properly when it is hot. Remember that a complete alignment procedure will destroy all data on the bubble. Any important data needs to be saved. Run all diagnostic tests on the hard disk interface and controller to assure that there are no failures other than misalignment. Collect your alignment tools. You will need hard disk diagnostics and a diagnostic manual, a non-metallic alignment tool, a frequency counter, an oscilloscope with at least 60 MHz bandwidth, and 3 calibrated ×10 test probes. Use your diagnostic program or documentation as a guide for test points and procedures. Perform the alignments in order. Start with motor speed on all drives and then align the VCO. Format the diagnostic track and continue with data pulse width, derun, and error amplifier adjustments. Remember to check the motor speed again for drift before finishing. When you finish the alignment, always reformat all drives and test the system thoroughly. Testing procedures will be covered in detail later. This completes Section 1 of this presentation. Now stop the tape and complete Section 1 in your workbook. In the first section of this tape, we discussed the theory of hard drive alignments. Now, let's look at some examples. This is a 12 meg external tandem hard drive with an 8X300 controller board. First, make sure that all technical bulletin modifications are present. Next, turn on the hard drive and let it warm up for 30 minutes. While waiting for the bubble to warm up, run all interface and controller diagnostics. Also, warm up your scope and frequency counter and check and calibrate your probes. Check the power supply voltages on each drive. The measured output must be at least the specified value. Measure the noise on each power supply with your scope. Consult the service manual for the acceptable range. Now, let's check the motor speed. Set your frequency counter to measure period in milliseconds. Do not use an oscilloscope. It is impossible to adjust the speed accurately based on a scope's analog visual display. Attach your counter probe to the index signal on the controller board. Check your technical bulletins for the correct test point. Use your diagnostics to select the drive you want to test. No index pulse will be gated onto the board unless the drive is selected. Select negative trigger on your frequency counter and adjust until the display stabilizes. Consult a hard drive service manual for the correct speed range for each drive type. If the speed is out of range or at the edge of the range, adjust it. Drive speed is usually specified in rotations per minute. To convert this to milliseconds, first divide the speed by 60 to get the number of rotations per second. For instance, if the specified speed is 3600 RPM, the spindle turns 60 times a second. Convert this frequency, 60 Hz, to period by dividing it into 1. In our example, a speed of 3600 RPM becomes a period of 16.7 milliseconds. Repeat this test for each hard drive in the system. Once all drive speeds are correct, continue to the controller adjustments. Remember that you must reformat the drive when you are done and that all data on the drive will be destroyed. Boot your diagnostics and select the drive menu. From there, choose the hard drive alignment procedures. Select the drive that you wish to test. Remember that under Tristos, the first hard drive is called drive 4, the second drive 5, and so on. The diagnostic will now ask whether you want to align a 5 1/4 or 8-inch hard drive. In this case, select option 2 for a 5 1/4-inch drive. The VCO alignment procedure will appear on the screen. The first step is to check for proper voltage on the VCO's fixed bias input. If this voltage is not correct, repair or replace the board before continuing. After verifying this voltage, check the VCO variable bias input and the output frequency. The diagnostic screen gives the test points and correct readings. Verify that your scope is set properly. Use ×10 probes DC coupled. Be sure that all calibrate knobs on the scope are in the locked position. Otherwise, the readings will be invalid. Adjust the variable capacitor for a stable 100 nanosecond square wave on channel A. Use a non-metallic alignment tool to prevent adding capacitance that might affect the alignment. Once the VCO output on channel A is exact, adjust the potentiometer to obtain the correct voltage on channel B, which is the VCO variable bias input. Next, turn the hard disk off and back on. Make sure that the VCO output on channel A locks in at the correct frequency. After power cycling the hard disk, you may have to reset the diagnostic by exiting to the main menu and reselecting it. The next adjustment on the 8X300 board is the D-Run one-shot. This alignment requires read data to function, so format the diagnostic track before attempting this alignment. Attach your scope probe to the output of the D-Run one-shot and set the scope as described in the diagnostic. Be sure to use negative slope and normal trigger. Also, make sure that all calibrate knobs are in the locked position. The signal will look somewhat unstable. Adjust the potentiometer so that the pulse is solidly low for the time specified by the diagnostics. In this case, the pulse should be 250 nanoseconds long. Always measure from the halfway point on each edge of the waveform. Keep in mind that you are adjusting for pulse width, not stability. A stable, repetitive D-Run pulse indicates incorrect alignment. Once the alignment looks correct, continue to the dynamic error amplifier adjustment. This alignment fine-tunes the VCO frequency to match the incoming data as closely as possible. Attach your test probe to the VCO control input. Your diagnostic will tell you what test point to use. Your scope will display a DC voltage of about 2 volts. The exact level is not important, but it must not be 5 volts or ground. The voltage displayed will also contain some spikes. Each one indicates a correction to the VCO's output frequency. Adjust the voltage for the smallest possible spikes and an equal number of pulses above and below the average level. Remember that a solid DC line indicates an incorrect alignment or a failing controller board. A correct reading will always contain some correction pulses. The pass counter on your diagnostic is a good indication of whether or not the alignment is correct. If it is incrementing quickly and steadily, the drive is reading properly. If the counter is incrementing slowly, the drive is reading data poorly or not at all. Reformat the diagnostic track and try the alignment again. Once the alignments appear correct, reformat the diagnostic track and check them again. Measurements that are within specifications and a rapidly incrementing diagnostic read counter indicate a correct alignment. After alignment, you must reformat all system hard drives. During alignment, you change the motor speed and read data timing. Reformatting is the only way to assure that the controller can read data on the bubble reliably. Before we cover final testing procedures, let's look at another example of a drive alignment. This is a Tandy 6000 with an internal 15 megabyte hard disk and WD-1010 controller. As in the previous example, we will check the system for mandatory modifications, warm it up, and run all diagnostics before we begin the alignment. The hard disk controller board in this system is in the 6000's card cage. We must place it on an extender board so that we can reach the test points and adjustable components. Always adjust internal hard disk controllers with all of the customer's boards in the card cage. Varying the load on the power supply by adding or removing boards will affect VCO operation by changing its input bias. As in our previous example, check the motor speed of all drives first. The procedure is exactly the same. Monitor the index pulse on the controller board with a frequency counter and select the drive that you want to check. If the motor speed needs adjustment, remove the hard disk from its casing so that you can reach the motor speed potentiometer and the index test point on the drive. You may set the bubble on its side for easier access, but do not run it upside down or you will damage the bearings and heads. Connect power to the drive using an extender cable if necessary. Use your frequency counter to monitor the period of the index pulse on the bubble you want to adjust. Rotate the potentiometer until the speed is in the middle of the range specified by the drive manual. Leave the bubble out during the alignment so that you can check for speed drift just before you reassemble the unit. Use the procedure in your 8-inch systems manual to align the controller board. This board has a test jumper that must be moved for the first 2 steps of the alignment. Turn the computer off, move the jumper, and turn the unit back on. Hold down the break and repeat keys until the Insert Diskette message appears. The first adjustment to make is the Read Data Pulse Width. Connect your probe to the test point listed in the diagnostics. Be sure that you are using the procedure for the correct revision of the board. This is very important since the test points vary from revision to revision. Adjust the potentiometer for a 75 to 80 nanosecond pulse, measuring from the 50% level. Be careful not to unseat the extender board as you turn the pot. Next, check the D-run signal and make a course adjustment. Attach your scope probe to the D-run output of the WD-1100 and look for toggling. At this point, don't try to fine-tune the signal, just make sure that it is a pulse and not a DC level. This completes the preliminary adjustments. Now, turn the unit off and return the test jumper to its normal position. Power the unit back on and adjust the VCO as described in the manual. This alignment is very similar to that on the 8X300 board. Channel A monitors the VCO's output frequency and Channel B its input bias. On this board there is no potentiometer, only an adjustable capacitor. Align it so that the VCO frequency is directly on specification and the DC bias is as close as possible to the center of its range. As on the 8X300 board, turn the unit off and back on to verify that the VCO locks properly. The last adjustment on the internal WD-1010 board is the Fine D-Run Adjust. Boot your diagnostic and select the hard disk alignment procedures. This adjustment requires read data, so format the diagnostic track and then execute continuous reads on it. Since the D-Run one-shot is inside an LSI chip on this board, we cannot monitor its output directly. Instead, we will adjust it so that there is one D-Run pulse for each sector on the track. Attach Channel A to the index pulse and Channel B to the D-Run signal. Check your diagnostic manual for the correct test points. Set your scope for negative trigger on Channel A, 2 millisecond per division, and 2 volts per division on each channel. Turn the D-Run adjustment pot until you can distinguish 17 D-Run pulses on Channel B between index pulses. Once this adjustment is correct, the read diagnostic should increment quickly with no errors. Now, recheck the motor speed on each drive. If the speed is drifted, adjust it and repeat the controller alignments. Once all adjustments are correct, reassemble the system. Before returning any unit to a customer, thoroughly test the hard drive using the HD REL diagnostic. Disable retries if the controller board you are using supports this option. This prohibits the controller from retrying on its own without reporting the error. First, select the Write Read Verify mode. Select the Single Pass and Test All Tracks options. This will verify that the write circuitry is working. When this test is complete, check the drive's data retention capabilities. Select the Read Only and Continuous Passes option for an extended test. Request the Random Read test, which checks all tracks out of order. This test exercises all hard drive systems more vigorously than sequential reads do. Let this test run as long as you possibly can. Some drives appear to function right after writing or formatting, but lose the data as time passes. At the end of this test, check the history table. See if all errors occurred on tracks listed as flawed on the media error map. If a few extra flawed tracks have appeared, add them to the drive's error map. If the number of new flaws is excessive, exchange the bubble. Reformat the drive and install the customer's operating system. Make sure that the system boots and operates properly. Always park the heads before turning the hard disk off. You may use either Xenix or MS-DOS to park the heads. If you prefer, boot the hard disk alignment diagnostic and seek the innermost track on the drive, then immediately turn the unit off. If the drive has a lockdown bracket, install it too. It is a good idea to remind the customer to remove the bracket before turning the hard disk on. This is the end of the Tandy Radio Shack hard disk alignment training tape. The knowledge gained from this presentation will help you to align all hard disks quickly and efficiently. For more information on hard disks, consult your technical bulletins, your diagnostic manuals, service manuals, and the workbook accompanying this tape.